In the lesson 4.4 example, are more males or females left-handed? We're going to check for independence. We're going to do this using a table. We want to know if there's a relationship between gender and handedness. To find out, we chose a simple random sample of 100 high school students from Australia who completed a survey. The two-way table summarizes the relationship between gender and dominant hand. We want to know if the events male and left-handed are independent. Basically, what independent means is we have to ask ourselves the question, does knowing if a student is male give us any more information about the probability of them being left-handed or not? If the answer is no, that being a male has no effect on the probability of being left-handed, then the two events are independent. If being a male makes a student more or less likely to be left-handed, then the two events are dependent. So let's take a look at the table. We can see from the table that out of the 46 males, 7 of them are left-handed. That's 15.2%. Symbolically, we can write it this way. The probability of left-handed, given that the student is male, is 7 out of 46, or 0.152. Let's compare that to another group, the females. 3 of the 54 females are left-handed. Now what we see is that's only 5.2%. Symbolically, again, the probability of left-handed given female is 3 out of 54. What we see is that knowing that a student is male gives us information about the likelihood of left-handedness. It increases the likelihood of left-handedness. If we didn't know whether a student was male or not, and just said we were going to select a student at random, the probability of being left-handed would be 10 out of 100, or 10%. That number jumps to 15% if we know that the student is male, and drops to 5.2% if we know that the student is a female. For this reason, based on the inequality of 0.152 and 0.052, the events male and left-handed are not independent. You can practice problems like this in your textbook by trying exercise 9 in this section.